international, military to human security threats we all are facing? Then welcome to this channel, Threat, Security and Technology. In this video, we will consider the dual nature of quantum technology, both in enhancing security as well as creating new threats. We will also consider quantum security ecosystem from geopolitics to global and national threats, military and homeland security to technology and industry. Hello, I am Rajesh Uppal, Director, International Defense, Security and Technology Incorporated, a think tank in California, US, with aim to promote awareness on international defense and security issues and their technology solutions. I have also founded US-India Science and Technology for Security, with aim to facilitate US-India academia and industry collaboration on security systems and technologies. I was Director, System Analysis, Safety, Quality and Reliability in Indian Defense Research and Development Organization, New Delhi, before I moved to US. Let's now consider the technological aspects of quantum technology. Quantum technology applies quantum mechanical properties such as superposition, entanglement, no cloning theorem on quantum systems such as atoms, ions, molecules and photons. Quantum bit is a basic unit of quantum information. Whereas in a classical system, a bit had to be either in one state or another, a quantum bit can simultaneously exist in large number of states, a phenomenon called superposition. Quantum entanglement is a phenomenon so that entangled particles remain connected in a sense that action performed on one affects the another, no matter what is the distance between them. No cloning theorem tells us that the quantum information or qubits cannot be copied. Quantum technology will have many applications which can be classified into three major classes. First is quantum computing and simulation. Quantum computers will bring power of massive parallel processing, equivalent to supercomputer on a chip. Quantum computers can consider large number of solutions simultaneously, quickly converge to the correct solution without needing to check each one individually. This dramatically speeds up certain problems such as number factoring. Quantum computer is also many types. First is a digital quantum computer, also known as gate level quantum computer, which is universal programmable computer, which will be able to execute all quantum algorithms and will have many applications. The power of quantum computer depends upon number of qubits and their quality, measured by coherence time and gate fidelity. Qubits are very fragile. They are easily disturbed by small temperature changes or vibration. Coherence measures the time during which quantum information is preserved. Gate fidelity measures the distance from ideal gate to decide how noisy the quantum gate is. We are now living in an era of noisy intermediate scale quantum or NISQ era, in which quantum computer contains hundreds of noisy qubits which are not error corrected. These qubits are realized generally through superconducting Josephson junctions or trapped ions. Some other promising qubits are topological qubits, semiconductor qubits, and photonic qubits. Calculation using these noisy qubits can cause errors and also make long computation impossible. However, these quantum computers can still demonstrate advantages of quantum computing, and researchers are developing algorithms in disciplines such as machine learning, quantum chemistry, and optimization. For future fault-tolerant quantum computers, researchers have developed error-correcting codes such as surface codes. These codes store data redundantly, with information spread over 10 of thousands of entangled qubits. This collection of qubits is known as one logical qubit or perfect qubit. Previous research has shown that a quantum computer with only 300 perfect qubits will be able to do more calculation in an instant than there are atoms in the universe. There is another kind of quantum computer called analog quantum computer, which performs quantum annealing. This computer can find the global minimum of a complicated mathematical expression exponentially faster than classical computers. Therefore, it is useful in optimization and sorting problems. Prime example is D-Wave system, which has got a 5000 qubits and is now planning for 7000 qubit system. Another quantum computer is quantum simulator, which is non-programmable as well as built for a single purpose. It is generally used to simulate other quantum systems which are generally less accessible. Since quantum computers work differently than classical computers, they require different software approach and quantum algorithms. One of the famous algorithms is Shor algorithm, which does integer factorization in polynomial time compared to exponential time taken by best classical algorithm. Another famous example is Grover's algorithm, which provides quadratic speedup in database searching. Quantum software development kits and computational platforms are being developed for users to develop and test their quantum algorithm. The next application area is quantum communications and cryptography. Quantum communications refer to quantum information exchange that uses photons as quantum information carriers over optical fibers or free space channels. At present, quantum data transfer rate is quite low, so it is not possible to encode entire messages. Therefore, quantum cryptography or quantum key distribution QKD is being used that uses single or entangled photons to generate a shared secret key between the parties, which is perfectly secure. The security is guaranteed by Heisenberg's uncertainty principle, which states that any attempt to measure or intercept the quantum transmissions will lead to enormously high error rate on the transmissions and hence will be detectable by the parties. QKD technology requires single photon sources, single photon detectors, modulating schemes, and protocols. Sensitive superconducting detectors also require cryogenic refrigerated devices. Point-to-point fiber optic QKD links are commercially available. However, they are of limited distances because of photon losses. Further, they are also being tested on free space channels from ground to satellites and drones. Further, these point-to-point links are now being expanded to QKD networks using quantum repeaters and quantum switches. QKD systems have been shown to be unconditionally secure, but that's only true for ideal systems. Their practical implementation have been shown to be vulnerable to many attacks, such as photon number splitting attacks that uses extra photons generated from quantum single photon sources, Trojan horse attack that uses transmissions on quantum channel and analyzes the back reflections. Another is the laser attack that blinds the quantum detectors. Researchers are now developing new QKD systems. One is measurement device independent or MDI QKD system that removes all detector-based side channel attacks. However, it is still vulnerable to source-based attacks. Another important element of quantum cryptography is quantum random number generator. The security of our cryptography depends upon generating strong keys that can only be achieved by truly random number generators. The weakness of random number generator can be exploited by the hackers to guess or steal the keys. Quantum random number generator is a true random number generator that is hardware based and employs randomness of quantum physics and can be used to generate hack-proof messages. The third important quantum application area is quantum sensing and metrology. Quantum sensing exploits high sensitivity of quantum systems to external disturbances to develop highly sensitive sensors. They can measure quantities such as time, electric and magnetic fields, inertial forces, temperatures, and many others. They employ quantum systems such as NV centers, Rydberg atoms, trapped ions, and atomic vapors. Quantum clocks can even improve the current atomic clocks that are based on cesium and rubidium and only lose 1 second in 100 million years. This next generation of clocks based on single atoms will lose only 1 second in a billion years. Quantum gravimeters can measure gravity with high sensitivity and reliability, and they are also immune to external noise sources. The quantum navigation can be far more accurate than current existing gyroscopes and accelerometers. It can provide backup to GPS if GPS fails, or navigation in areas where GPS is not. Quantum imaging exploits quantum entanglement of electromagnetic field to image objects under very low light levels, or where in presence of strong background illumination. It has applications in 3D cameras, behind the corner cameras, quantum lidar, and quantum radar. Let us now explore quantum geopolitics. The global quantum computing market is expected to reach 14 billion US dollars in 2025. In the same period, quantum cryptography is expected to reach 25 billion US dollars and quantum census market up to 700 million US dollars. The quantum technology is a dual use technology. It is used both in commercial and military application, has both risk as well as opportunity. Quantum technology is expected to revolutionize warfare by providing new capabilities such as quantum computer, quantum radars, quantum key distribution, as well as enhancing existing technologies such as quantum optimization, quantum machine learning, then enhanced sensing capabilities, cryptoanalysis, enhancing the accuracy of position, navigation, and timing services. The economic and military advantages are driving intense quantum race among countries led by China, United States, Europe, Canada, and Australia. In a race to develop first large-scale programmable quantum computer, Google took the lead in 2019 when it launched Sycamore, a 53-qubit quantum computer. Further, it claimed quantum supremacy by completing a task in 200 seconds and estimating that the supercomputer Summit would do the same task in 10,000 hours. Recently, IBM introduced a 127 physical qubit Eagle quantum computer. Expectations are that we will reach around 1 million physical qubits in 10 years. In 2021, China claimed to have tested 2 quantum computers on a task that were more challenging than Sycamore and achieved faster results. In one study, they tested Sukonzi, a 56 semiconductor qubit quantum computer, on a task of sampling a given spread of probabilities. In another study, they studied Zhuzhang 2.20, a photonic quantum computer, on a task of Gaussian boson sampling that analyzes a random patches of data. They claim that it takes 10 exponential 24 times faster than any classical supercomputer. China claimed that their work points to unambiguous quantum computational advantage. Coming to global quantum communication race, China has taken clear lead, with other countries including US, Europe, Canada, and Japan trying to catch up. China has established 2,000 kilometer quantum fiber optic network that links 4 quantum metropolitan area networks, and they have also completed a 2,600 kilometer quantum satellite link between 2 observatories. The quantum fiber network comprises of 700 optical fiber links supported by 32 trusted relay nodes and serves around 150 users. China was also first country to launch a quantum communication satellite in 2016 known as MESSIAS. They established a secure satellite link between two Earth stations separated by 1100 kilometers using entangled particles for simultaneous transmissions of keys. They have also carried out tests of first quantum secured video call. Pan and his colleagues are now going to launch a constellation of satellites and nationwide fiber optic networks to create unhackable quantum computer network. The military is also likely to transition its networks to quantum networks and make them hackable. Quantum gravity sensors, quantum navigators, and quantum imaging systems are now available and being transitioned to commercial products. Another key factor of winning global quantum race will be development of quantum literate workforce. Countries have launched various initiatives for developing domestic quantum workforces and developing new quantum technology industry. Let us now explore the role of quantum tech in global security. We saw earlier that quantum computers will bring power of massively parallel processing. They can process huge data sets in a fraction of a second, what would have otherwise taken days or weeks. This has application in big data analysis, searching through huge unstructured and unsorted data, and discovering patterns and anomalously extremely quickly. Quantum technology will enhance global security in many ways. These include disaster prediction, combating global warming, improving the manufacturing processes of steel, cement, and fertilizers, secure communication. They can discover new efficient catalytic processes, creating new efficient solid-state batteries. Then climate change mitigation by removing carbon dioxide from our atmosphere. They can also detect, weed, analyze possible catalyst combinations, and come up with effective fertilizers. Quantum computers can simulate quantum systems such as electrons and molecules. To simulate a system of n electrons, quantum computer requires only n qubits compared to 2 exponential n classical bits required in a classical computer. They can simulate electron structure of materials, leading to discovery of new drugs, chemicals, and materials. These include room temperature superconductors, semiconductor materials, lighter and stronger materials that requires less carbon to produce, that will result in lower emissions from our buildings and transportation. Scientists at Harvard have found that quantum computers will allow us to map proteins in the same way like we do genes today. Manton AI has discovered new proteins using quantum hybrid programs that are useful for live virus testing against COVID-19. Another important research direction is quantum artificial intelligence machine learning or quantum enhanced AI. Machine learning nowadays is being applied in large classes of real world problems. However, it requires large training time because of size and variety of data required for its learning. Quantum computer can significantly decrease the training time of machine learning by providing quantum speedup of its optimization subroutines. For example, quantum enhanced AI can be used to build better classifiers for speech recognitions. Google and NASA are exploring its potential for web search, speech recognition, planning and scheduling, air traffic management, robotic missions to other planets. NASA hopes that quantum computers will help schedule its rocket launches, simulate its future missions and spacecraft. Let us now explore whether quantum can be a global threat. First, examine the role of quantum in cybersecurity. Cybersecurity has become very important as number of attacks and their sophistication is growing, and cyber warfare is being used by adversary to target critical information infrastructure like health systems, electricity grids, telecommunication, and banking. The quantum technology is both a cyber threat as well as it can provide quantum security and unhackable communications. For example, since quantum computers will multiply the power of AI, they can accelerate the development of automated cyber defense. Quantum computer will also be a threat to our cyber security. The security of our critical information infrastructure depends on cryptography to provide services like confidentiality, integrity, authentication, and non-repetition. The cryptography involves encryption at the transmission, which uses a key to convert ordinary text into a secret code. At the receiver, the opposite is performed. The secret code is converted back into original text using another key. The public key crypto system uses two keys. One is called public key that is used for encryption at the transmission, that is available to all, and another is the secret key that is used at the decryption called private key. The security of these public key crypto systems depends on difficulty of integer factorization, of decomposition of number into large prime factors. However, security of these algorithms is vulnerable to progress in computing technology, development of new algorithms, and also progress in quantum computers. A quantum computer of sufficient size will be able to execute Shor's algorithm and will be able to factorize large prime factors in matter of hours and days, which a classical computer would take billions of years to compute. According to Bart Praneel, professor of cryptography in Belgium, to crack a 1024-bit encryption key, you will need 2048 ideal qubits. We saw earlier that error correction codes produce a single ideal qubit by linking tens, thousands of physically entangled qubits. That means we will need millions of physical qubits. That means that quantum computer won't be a threat to cryptography very soon. However, threat also exists now. According to intelligence agencies, adversarial nation states are storing the encrypted data, waiting for the day quantum computer will be able to crack them. The threat also extends to military data, which will impact the security of military missions. The data security also needs to be available for 10 to 50 years. Therefore, organization should start planning now. Therefore, organizations are pursuing two solution approaches. One is post-quantum cryptography or quantum resistance cryptography, that is developing new cryptographic algorithms that will be safe against both classical and quantum computer attacks. This is the approach followed by National Institute of Standards and Technology NIST through a competition which in third stage has identified three candidate algorithms: elliptic, multivariate, and code-based. The adoption of quantum resistant cryptography will be a complex and long process and is expected to take 20 years to complete. In contrast to threat posed to asymmetric cryptography or public key cryptography, the symmetric cryptographic algorithms are relatively safe. In spite of Grover's algorithm of quadratic speedup of attacks against symmetric ciphers, the doubling the key length can effectively block such attacks. AES 128 and SHA 256 are therefore quantum resistant according to NIST evaluation criteria. The other solution is a hardware-based approach for quantum cryptography, which we saw earlier, uses laws of quantum physics such as Heisenberg's uncertainty principle and no cloning theorem to guarantee security. QKD uses single or entangled photons to generate shared secret key between the parties that is secure even against quantum computer attacks. Communication using QKD can be delivered through fiber optic networks or over the air through drones and satellites. The limitations of QKD are limited transmission speed and distance, high cost of dedicated hardware, and requirement of quantum repeaters. Most current quantum QKD fiber optic links are limited to around 300 to 600 kilometer distance due to losses in the fiber. The next aim is to extend these point-to-point QKD links to national scale multi-user QKD networks. However, quantum signals cannot be amplified like electronic signals. Therefore, these networks requires development of quantum repeaters or quantum memories. However, no reliable quantum memory is available yet. The next revolution the countries are working on is quantum internet. Quantum internet will employ entanglement to enable quantum communication applications between any 2 points on the earth. It will comprise of quantum computers as end devices transmitting qubits, which will be processed by quantum switches, hubs, and routers. Quantum internet will have many applications, such as transmitting large amount of data across immense distances very securely. It will multiply the power of quantum computers and quantum sensors by linking them together. For example, synchronization of atomic clocks all over the globe or detecting gravitational waves. However, Neil Johnson or George Washington universities and others have worked out how terrorists could disrupt such a global quantum internet almost instantly and without revealing their identity. They model the quantum internet as quantum cloud of entangled photons, in which users inject their photons carrying quantum information. If 3 or more attackers inject random information into the network at the same time, it will become entangled with the rest and disturb the global quantum state. In that case, we cannot retrieve the initial state even in the principle. Quantum technology will also play a critical role in national security. Quantum computers can calculate any kind of risk, such as those of approaching hurricane. It can perform optimization, such as logistics or traffic, preventing congestion. It can improve the self-driving car technologies. QKD will improve the security of law enforcement, financial transactions, electoral or government communications. Quantum sensors will assist in counterterrorism operations such as detecting hazardous gases, buried mines or IEDs. Quantum imaging camera will be able to detect terrorist activities beyond line of sight, such as around the corners or through the buildings. These technology will also improve self-driving car technologies by making them safer. Quantum imaging also enables seeing through scattering or obscurant media such as fog, smoke or dust, or under very low light conditions. This is highly useful in cases such as helicopter landing on sandy environment, which generates a lot of dust, affects pilot visibility and leads to accidents. Quantum imaging therefore can prevent accidents of helicopter in such degraded environment. We saw earlier that malicious actors in possession of quantum computer will able to bypass traditional security, decrypting information and communications. So NSA is therefore advising transition to post-quantum cryptography. On the other hand, NSA and other spy agencies are giving thrust to development of quantum computer so as to be able to break the encryption of terrorists and adversaries to fulfill their role of protecting the society. Let us now explore the role of quantum technology in future military battlefield. We saw earlier that quantum computers will be able to crack cryptography of adversaries' communications. It will multiply the power of artificial intelligence for improvement of situational awareness, mission planning, and automating cyber defense. Quantum optimization will lead to improvement in military logistics, war games, system verification and validation, planning supply chains, as well as designing new weapons and platforms. Quantum computers can assist in chemical, biological, radiological, nuclear, or CBRN defense by simulating and analyzing new CBRN threats. They can assist in making new materials for military, such as stealth, camouflage, armor, or even hypersonic weapons and platforms. QKD is now tested by militaries in the battlefield. Navies are planning to extend the range of QKD networks to even ships through satellites. Submarine communication is very critical for maintaining nuclear deterrence capability. Researchers are now developing QKD secure communication between submarines, between submarine and other subvessels, aircrafts, or even satellites. Currently, submarines use ELF or VLF waves as they are the only low frequency waves that can travel in the water. However, they are vulnerable to interception by adversary who can know their location and sink them. Quantum sensors will outperform current sensors and will provide dramatically improved performance in critical military missions. Rydberg atoms have extreme sensitivity of electric field, including microwaves from 100 MHz to 1 THz. They will enable development of micrometer size antennas for communication, radars, and electronic warfare systems for full range of frequencies. Quantum radars will be able to detect stealth aircraft. Quantum radar use entanglement of two photons in which one photon is transmitted towards the target and other is kept captive for observation. As the transmitted photon bounces off the target, its behavior is being monitored by the captive photon. This results in very high sensitive observation of targets which was not available in earlier radars. Another advantage is that quantum radars emit very little radiation, hence very difficult to detect. A Chinese company, Electronics Technology Group Corporation, claims to have developed a quantum radar which will able to detect US stealth aircraft such as F-22 Raptor and F-35. Further, it claims it can also detect type of aircraft and weapons it is carrying. Another important area for quantum sensors is navigation. The current navigation is dependent on global positioning systems or GPS. However, GPS is not available in underground and underwater application and is also vulnerable to jamming, deception, and spoofing. Quantum sensor will be able to provide critical timing at positioning, accuracy in GPS denied and GPS challenge environments. Quantum accelerometers and quantum inertial navigation devices offer very less drift, of the order of 100 meters in a month. Further, they are getting miniaturized to be deployed on drones and missiles. Quantum navigation enables submarines to hide better. On the other hand, other quantum sensors like quantum magnetometers, quantum gravimeters, and quantum clocks enable us to detect submarines better. The quantum clocks will improve the spatial resolution in GPS, navigation, and precise targeting. Their very high stability allows clocks to be used as ultra-sensitive sensors of magnetic and gravity fields. They can detect even minute gravitational anomaly caused by clocks being lifted by just 1 foot. This allows military personnel to detect underground structures, hidden weapons, and submarines. Quantum gravimeters based on atom interferometry promises airborne detection of underground structures, nuclear stockpiles, and nuclear submarines. Quantum magnetometer, such as superconducting quantum interferometry device or SQUIDs, promises ultra-high sensitivity and large area search of the oceans. Scientists at Chinese National Academy of Science have claimed to develop SQUIDs that can detect a submarine 6 kilometers away. It is also developing an airborne version, the submarine Star of Death, which could cause increased vulnerability of US submarines. Quantum gravimeters and magnetometers will enable long-range standoff detection of military targets based on their gravity and magnetic signatures. Large structures and vehicles generate unique gravity signature based on their mass, or magnetic structures based on their metallic composition, which can be detected. Let us now consider how this quantum technology will be the critical enabler of emerging multi-domain battlefield that includes land, sea, air, space, and cyber, along with hybrid warfare, information warfare, and cognitive warfare. Quantum computers will enable big data processing of large number of intelligence, surveillance, and reconnaissance assets. Quantum enabled machine learning and AI will allow detecting targets, discriminating between targets and decoys. Further, these AI enabled quantum computers will become extremely powerful when they are combined with vast data set received through powerful quantum sensors. This will dramatically increase our situational awareness, including detecting and localization submarines in vast oceans. Quantum communication will provide tamper-proof battle space communication, allowing platform to connect and securely communicate across all domains in a congested and contested. Quantum network of clocks will allow precise time and clock distribution with guaranteed security. It will enable new sensors such as multistatic radars and new concepts such as distributed electronic warfare, employing combination of land, air, sea, and space platforms. Quantum enabled AI and optimization will allow multi-domain command and control. That will allow commanders to simulate complex scenarios, evaluate alternative course of actions, and take optimal decisions. Quantum network will enable multi-domain synchronization among platforms, multi-vehicle swarms, weapons, and systems to deliver integrated effects across all domains. Therefore, experts have coined the term quantum warfare that requires development of new military strategies, doctrines, and policy, as well as ethics issues. For all of us, the most important is human security. That is freedom from threats to our lives, safety, and rights. On one hand, quantum technology would improve human security and boost human life expectancy through accurate and faster diagnosis of diseases, developing faster medicines and therapies for diseases like cancer and COVID-19, and personalized medical care. On the other hand, quantum-enabled AI will lead to development of lethal autonomous weapon systems that would make life and death decisions on their own. It could also accelerate development of artificial superintelligence systems, which could present existential threat to humanity according to some experts. It could also accelerate the development of fourth wave AI systems that would have common sense and would make decisions based on laws, ethics, and regulation and prevent their misuse. Thanks for listening. In future videos, we will continue to explore various threats, security, and technologies. You are welcome to suggest topics of your interest in the comments below. I would be happy to address them first. If you want to participate in this fascinating journey of threat, security, and technology, please subscribe below.